we stopped it on a simple demonstration last time to talk about how we define decision variable. So this time we directly look into something of the algorithm. So it's not about only you define the variables and define the objectives. So last time we talked quite much about how you define decision variable even using facts as an example. So for the first part of this lecture, we forget about facts about software. We mainly look at the algorithm. I promise to show you some algorithm that are so simple that you can put it in MATLAB in 5 minutes if you know about what you should do with your problem. So suppose you have your model, you have your evaluation function, you have your objective functions, then this will be two of the very simple algorithm that you can implement by yourself. The first algorithm is called a random search. So even though it's so simple, but still I think you will learn pretty much about how an algorithm works. And then hill climbing is more like an advanced variation of the random search. So what is random search? You start with the first iteration. You start with finding an initial solution. And this is something interesting to note in optimization, where you start to find your solution is something crucially important. And that's why in a lot of problem, they actually suggest the user to define certain solution if it is possible to be defined by a user to define where an initial solution should be started. Otherwise, if you don't have any good solution to start, then you will all the way rely on the randomization. And that's why you will just randomly choose a solution in your search space. And then if you randomly choose a solution, then of course the chance that you will hit your jackpot is very difficult. But anyway, we start with a solution x0 from your available solution set. And that was x as we tried to develop last time. So this is a set of possible solutions. And then the next step will be from the first solution, then you just randomly choose from all the feasible solutions, of course now except x0, otherwise you will just keep repeating the same solution. So you need to have a certain memory to remember what you have in x0 and then make sure that you randomly generate x hyphen. I don't know if you still have this memory. We talk about that the equality constraint is something very difficult to fulfill. And then we will also come back later. But remember, when we talk about all feasible solutions, we mean that solution that are bound within the constraints. So if you validate those constraints that we talk about, that we define in the mathematical formulation, then they are not feasible solution. And if it's a simulation based, then you run the simulation. But of course, if you have just a model, you have the calculation, then you calculate the value. So y is the objective function. So you calculate the function of x hyphen and then calculate the y value. And then if you find the new value, the y value is lower than the original, if we start with a 0, x0 means that were original solutions, then we will simply replace the solution with the x hyphen. That means the new solution that we find. Be careful that why this one hole here is because of we are doing minimization. So without announcing explicitly, normally for an optimization problem, it will be minimization. But of course, last time we already seen objective of maximizing the profit. But mathematically, usually we start with a minimization. And then this step will continue. You just make the iteration step improve. And then you usually have some kind of max car means your budget. So if you say that you will afford to have the J equal to, I don't know, 1,000, 2,000, or sometimes very heavy weight optimization, you may run to several tens of thousands. But I think it's very seldom you go for millions, as we talked about last time. for simulation is very expensive. So if you go for millions of J maximum count, then you will be very time consuming. And this is something we call random search. And then even though it looks to be very simple, but this algorithm actually illustrates to you how an basic algorithm work by showing this kind of pseudocode. And then if you want to really make it, it is possible that you can make it your own code in MATLAB or in Python. It's very simple, but you illustrate the principle. And you also illustrate another principle. Remember when we talked about last time that heuristics, in general, materialistic or heuristic, they don't guarantee, or in most of the cases, you will not find the mathematical optimal solution. The reason is also because of you just give a certain maximum count, and then if you elapse all those count, then your optimization will stop. So the best will be you find the best solution you find from this maximum count. And then you're also very limited to how you could do the randomization. So let's look at another form which look pretty similar, but there is some a big difference. The algorithm is called hill climbing. Again, we start with the initial solutions, but the difference here will be we choose another solution, x hyphen, which is from the vicinity. That means in the neighborhood of x0. Again, it's not mentioned very clearly, but how you find the closed solution, this is also technically how you define your hill climbing. But last we saw also to randomization, but we randomize within a certain range that we predefine closer to x0. And then again, the rest of the step looks almost exactly at the random search. Now, these two algorithms look to be too simple. And then you may ask, so if they are so simple, why don't everyone use them, or are they really useful? The answer will be very interesting to notice when we illustrate something called the search space. In order to be a little bit more clear, I think it's good to go back to that figure. We talk about the search space. We show this classical MATLAB figure to illustrate optimization. This will be the search space. So you have the search space here across X and Y dimensions. The theory is like that. If you use randomization, so instead of these mathematical functions, if you use randomization to generate your search space, that means your search space is actually generated by a random function. Then in theory, the best algorithm in the world that you can find the optimal will actually be random search. So whether an algorithm will be useful or not depends pretty much on the nature of the problem. And that's why, I don't cover this in my lecture. This is something very complicated, physical research there. But in physics, they have something called the no free lunch theorem. The theorem, the name of the theorem doesn't really tell you what exactly it means, but it actually means that there is no algorithm that can beat all other algorithms to solve all problems. And that means for a particular problem, the best way to find an algorithm is a customized algorithm or a limited range of algorithm that is not generalized to all problems, but customized to a specific problem. And then for hill climbing, you may also ask one question, as we also talked about last time, it could be easily trapped in the local optima. But if you are just choosing some solution from the vicinity, then of course it seems that it's quite easy to be trapped in somewhere location. Now, this is interesting that hill climbing is usually related to a mechanism we call exploitations. Later, you will hear me about the word explorations and exploitations. So in English, if I just read it, maybe it's a bit confusing, but I will continue to tell you why hill climbing is very useful if you want to do some deeper exploitations. But already now I can tell you a story. I know that there was a university developing an algorithm for Volvo powertrain some years ago about scheduling. and it was a mathematical based. But later I heard that the company didn't want to use the algorithm. The reason was because of whenever they change a little bit the demand, the input setting, the solution looked very different from the last solution, even though they made only slight changes. So now this is a typical situation in industry is they have some input, they have some background information, they put it into optimization. But later, after they run some optimization, they find that something have to change. And for someone already run an optimization, if the algorithm this time give you one solution, but next time give you a very different solution, then people will probably lose the credibility required in order to make the decision making. So that's why hill climbing is a classical algorithm. Whenever you already have one solution, but then you want to make sure that the solution does not really deviate, even though you still want to keep on running to get some better solution. But you simply don't want to get a very big surprise that you get a totally different solutions. We will come back to look about how hill climbing can be combined with exploration algorithm. We talk about genetic algorithms, and probably you already covered this in some other courses. I don't know whether it was an AI or even, I think genetic algorithm is so popular that you might already have heard about or read about in other courses. Now, the original version was defined by John Holland, and this is, I think John Holland passed away some years ago. Otherwise, I think he was still a legend in the history of optimization. He was a professor of psychology, so he was not any mathematician or computer scientist. He was a psychologist. But I think he was very active until the day when the last time I heard about him, it was 2015 from someone in USA talking about he was still active. I think by that time he must be 90, over 95 years old, but he still got very active to be consultant to big companies. So he defined the original version of genetic algorithm 1975, but that first algorithm was more like quite theoretical. So there was not too much application, especially not too many applications, example in engineering. So his student, David Goldberg, which actually was the supervisor of Professor Kaimoy Depp that I mentioned about last time. We will come back to talk about who is Professor Depp and then what is his algorithm for multi-objective. But anyway, David Goldberg was his supervisor. So in 1989, he published a book, and that book is about genetic applications, genetic algorithm applications to engineering. So David Goldberg was a civil engineer in the beginning, but later he became a computer scientist, mainly tried to promote genetic algorithm. And then he retired pretty early. So I met him once in, I don't remember now, 2013 in Italy in a conference. But by that time, he already retired. Now, go back to the algorithm. The basic elements, what we call genetic algorithm, last time we talked about something very important, population based. And you can customize, you can change a lot of things in the middle of the algorithm. So you can have a lot of customization. Even you can try to avoid randomization or to increase some other randomization. You can play along quite much. But the thing that you cannot remove from a genetic algorithm, you must be population based. And then you may ask, what happens if you really take away the populations? Then you have another algorithm called the evolution strategies from Germany, almost the same time as John Holland, but then that, even though it's also based on evolution and also based on some sort of randomization, but the population based means a genetic algorithm was unique compared to other evolutionary based algorithm. And then deviation-free stochastic. This one is a little bit more complicated. You talk about that. You try to borrow the common brief about natural selection and the evolutionary processes. I'm quite sure that for the students who are today, I'm quite sure that you none of you really study biology before. I don't expect that. I know that some students in Stockholm, they study economics before they become a medical doctors, but I don't know about the background of you, but I don't know how many of you really have things related to biology. So today, I think it's still a strong debate whether biology, that means the evolutionary process is something directed or totally randomized. I think it's still a very hot debate. So if you ask me my personal opinion based on what I read and also what I believe, I think that the evolution process some sort directed instead of a totally random. But anyway, I think for putting into the algorithm, then we don't really need to bother whether the biology concept is really 100% followed. So if we believe that the natural selections and the average process is something based on purely of randomization, then we just put it into the algorithm. And then because of we have the randomizations, and then it's not based on any information related to the gradient, like you do in calculus, about the slope we talked about last time about a car. That means it's much more flexible and also more generic. And the genericity usually associated with how you cook your solutions into something genotype. And then you need to translate, go back to your phenotype. Phenotype means like what means in the real world. So in the real world, you have the number of machine, number of workers, and in the hospital, you have a number of doctors, which is your decision variable, one of the decision variable. But when you convert this variable into the genotype, for the optimization, you will process the genotype pretty much about when you talk about DNA. So we borrow the concept from the evolution process, and then we will come back to talk about exactly what this natural selection play its role in the algorithm. So population base, we talk about that, but then exactly how it works, I think we have some more example later. It is easily applicable to both continuous and discrete optimization problem. So in this sense, it's already much more flexible compared to other mathematical programming. For example, like linear programming, you can only work with continuous variable. And then the stochastic transition rules, that means through randomization, you will test a large number set of solutions in the populations. Will also make it easily to get rid of the local minima problem. Of course, there will be a cost there. So it is not something that without a cost. So genetic algorithm is generic, but at the same time, it will take also longer time to run, especially for a generic problem. The reason was because of you rely pretty much on the randomization and also try out many different solutions. So that's why highly flexible compared to other optimization algorithm. And also not only is it compared to other algorithm, but you can also easily combine genetic algorithm with other optimization, which we will show later. So remember some of the keyword, and then let's look at further on to talk about how this chromosomes works, and also to look about how this natural selection work with what we call the fitness value. So when we talk about the genotype, the technical term which we borrow from DNA is a chromosome. And chromosome means that we simply not only about one variable, but multiple variable, we put them together and then put it into encoding. It will be a finite length of a string of alphabets. But normally in an original genetic algorithm, we start with a binary string. And then later, when we give the example about the crossover mutation, we also stick to this binary string and see how it works. And then the alphabet by the representation is called the genes, and then the value of the genes, that means representing the value of the decision variable will be called the alleles. But usually, after you start to use genetic algorithm, you seldom go back to look at those terms in this level. But the fitness value is very important because the fitness value in most cases is connecting to the objective functions. And that's why it's a y of your input vector, your decision vector. Your decision vector, you put it into the y functions, you calculate the objective function value, and this will be, if you translate it back to genetic algorithm, this will be the fitness value. And then normally, now this is the case that we looking at the highest fitness. And then in this case, if your objective function is maximized, then of course the fitness value is the higher will be possible. And then the population, in this case, that means it's a pool of chromosome. And that means each population will contains of a population of chromosome when each chromosome also represent one single solution. That is what we mean by a population of solutions. And if you have a population concept, so when you move from one population, from one generation to another, it will be called a generation iterations. So the genetic algorithm will construct a new population using genetic and evolution operators. So we start with a pool of solution in a population. And then if we advance from one pool to another pool, that means one generation to another generation, we need to have some genetic operators. And these genetic operators, they are very important to genetic algorithm because without these specific operators, then of course they are a variant of genetic algorithm, maybe some sort of customization, but then it probably is not something that is proposed from the original version. So in the original version, you have selection, crossover, and mutation. Sometimes some people may ignore mutation. That means they simply take away one operations. But in general, without selection and crossover, then you can't simply call it a genetic algorithm. Maybe you call it some other population-based algorithm, but selections and crossover, they are pretty much a signature. And then in real life, in mutations, of course, here when we talk about mutation, we are talking about something positive that you will be useful because in real life, in biology or in human biology, so mutation sometimes relate to some bad thing. The extreme bad thing will be cancer. Of course, we are undergoing a lot of mutations every day, but some mutation will give you diseases. But in this case, when genetic operations, mutation is something good. And then why this is good, we will talk about later. The basic idea about selection, crossover, mutation is how you select a partial set of your chromosomes and then how you regroup them. So if you select them and call them parents, here as well, we borrow the terms from biology. And then if we have a parent, how we can produce the offspring from this parent using the concept of crossover. And then again, I think the whole idea is how you can make the fitness value to be higher so that it will be more easier to survive in biological term and UL terms. That means we are near to the optimal. So how to combine the best features of the parents in order to get higher fitness value. So in plain English, this is how the algorithm work. But of course, we shouldn't just look at the like English. We can look at some pseudocode. We borrow what we learn from random search. We start with some initial solution. But in this case, it will not be simple that you find one solution. You need to have population of solutions. Now, it is the same discussions when you have random search. You start with a one solution, but where you find this one solution? Okay, you may ask the user to give you one hint, or you may resort of some randomization, some other mechanism. So here is the same. You use a randomization, or you can also put into some of the solution. Now, because you have a population, that means that you can also include partially the solutions coming from the user and also partially of the solution coming from randomization. And this is very common because of this is exactly what we could do even with the software is you can start with design experiment. We talked about design experiment last time. And there are also some more advanced design experiment called the Latin hypercube design that you ensure that you can get better sampling from your search space. So if you fill in the population with the partially the solution coming from design experiment, you can also fill in the rest of the solutions in the population using randomization. So if we do not reach our whole total budget, again, this is materialistics. So we have a certain budget. Then we will use some iteration functions to iterate the populations. The idea is to get the fitness value of the populations. And then you run your selection so that you get your current generation is PT. And then you prepare your next generation PT plus run. But before you reloop this, you go back to run these iterations. You run the crossover and mutation before you can say that now you work on the next generations. So that's why the step here, iterating the fitness value, make the selection, do the crossover and mutation. They are the flow of a genetic algorithm. And this loop just continue and will be generation rise. So the loop here, they are performed per generation, not per solution. So things happen per solution will be happen here, for example. So you send the whole population to do the iterations. So if it is a simulation base, then you will run the simulation run for the solution one by one. But the process here in the loop here is population rise. And then before we continue, I think there is some theory. I think later you will see that I have go into looking into the selection mechanism. But then before we continue to talk about why genetic algorithm works better compared to other algorithms, is because of the theory concept by mineralogist since 1992. He had this explanation about comparing a general purpose search algorithm like a genetic algorithm. And then now this is the slide I compare with hill climbing and random search. Now, exploitation against explorations. And here, even we talk about single objective, it's interesting to know that how we can do the exploration to find new solution, even though our aim is to find a single objective. So hill climbing is a good example of a strategy that you explore, that you go deeper to find a better solution by possible improvement, but then you actually ignore the exploration of the search space because you always just explore the reagent, the vicinity of the solution that you have now. If you start with your initial solution, you still just exploring your vicinity, the neighborhood. That means you actually ignore the exploration of the whole search space. But this could, as we talk about, that it could be used to go deeper to find something nearby so that the user recognize the solution not too far away from what already have. But random search is now just too much. After you run one solutions, you have the chance that any other solution in the whole search space can be another solution. That means you actually have no control about what will you find the next. But it's very good because then you just explore your search space maximally. So that's why random search is another extreme example, but this time is about exploration. So all the general purpose search algorithm striking to combine the best elements using either direct or stochastic randomized search in order to make a balance between exploration and exploitation. And this is one of the signature of genetic algorithm that you see that is both a mixture of both explorations through you have the population base, you have the randomization, but at the same time, through combining the good features of the parents, it also try to maintain the good features or the mechanism that you already find to be good in the previous generation. So randomizations, yes, you can do it. And then there is also related to mutations. But then the selection and the crossover, they are there mainly to preserve the good features from the previous generation in order to allow to this doing exploitations. So this is a well balance between exploitation and exploitations. I have a one very good example to tell you. This is a real example how we did, even though it's already quite old now. I think this case study, wow, it must be finished 2008, so quite many years ago. But that example we applied to Volvo Aero. Now the company is called GKN Aerospace in Turretten. Now we show this is not combining them in an algorithm, but we show that how you could first using genetic algorithm to explore pretty much the search space, and then later what's the benefit if you switch to hill climbing. So this is not a uh, combination of merging these two algorithms into one algorithm. This is more about you running the first exploration first, and then you do the exploitations. And let's see the effect. The pink line there was from genetic algorithm. And then this, I like this slide because you show that the genetic algorithm in the beginning tried to explore pretty much. And you don't see too much about what they explore in the search space. I don't think I allowed to let you see all the details about the decision variable. But anyway, we call something called the fitness value, which relate to some objective functions. And by looking at how the genetic algorithm move up and down here, you could see that actually in the beginning, you try many different area, and then you get both good and bad. So some of them are good, and then in this case, we want to minimize. That means that you also go lower and lower. But through the signals, you could actually see that the even genetic algorithm try to do some exploration too quite much in the beginning. You could see that it actually tried to narrow down to we call convergence in algorithm terms. It converged into a certain fitness value, and then it still fluctuate a little bit, but the range is not as much as in the beginning. Now compare with the yellow line here, we start with a hill climbing. So of course, hill climbing is also steadily, if you look at the mean value, it's not so fluctuating. That means you keep on reducing the successfully keep on the reducing the value. Then of course, if the value is not reducing, then of course you will not remove, you will not continue, because you replace the current solution with a better solution with a lower value in the fitness value or objective functions. But if you compare later, when we switch to hill climbing, or in general, compare the pink line with the yellow line, you could see that the genetic algorithm already from the beginning already beat pretty well hill climbing, because the value is fine, it's much lower if we aiming at minimization. But then if we switch to after 200 simulations, I don't think this is a correct term. I think this must be something like 200 generations. And then we switch to hill climbing. And here you could find that is something very interesting to find here will be the hill climbing actually could find value lower than the genetic algorithm. So by applying hill climbing from the beginning, it will give you much inferior solutions compared to genetic algorithm. But if you first start with explorations and then later switch to exploitations, you could find actually even better value. And that is why in practical applications, it's also possible and common that people also switch the algorithm from one algorithm that is better doing the exploitations and later try to do exploitation. And hill climbing is a common algorithm. We have a technical term to call it, called a low-code search. So the low-code search means that you already find some good solution, and then you could try to find better. Before we take the break, I think it's good to give some idea about selections. We talk about John Holland. In his first proposal, already in 1975, he proposed something called a relative view selection. Suppose you get the fitness value of each individual because you made the iterations of the whole population, right? and then combine all the fitness value, and then the probability for a particular member to be selected will be based on this fitness value. And then we can make the calculations about this cumulative probability, we call it Q. And then we do a uniform random search in the range from 0 to 1. You get away 0, you don't allow to have any 0, but from 0 to 1, you run the uniform random number generations. That means the chance that you get any number between 0 and 1 will be equal. And then based on this cumulative probability that is associated with each solutions, then based on the random number you find R based on the which range. So then let's say that if R is lower than the Q1 value, when you make this calculation, let's say that R is lower than the Q1 value, then you will select the first chromosome. And then if R fall into the range of Qi minus 1 to Qi, then you will select the Xi solutions based on the way I here. In this case, it's more like you spread. I don't have a good figure now in here, but if you search volatility wheel selection, you will find some graphic example. But it's pretty much like you have if you go to an amusement park and you have a volatility wheel, then of course the solution that give you a higher fitness value, the chance that it will be selected by this mechanism will be higher. And then those solutions that have a lower fitness value will be selected, will be lower, because the area they occupy in this volatility wheel, if you spread it and into this from this range here, you will know that the chance that will be get lower if the fitness value is lower. And repeating this step a couple of times, if you want to have n solutions as the candidates in the mating pool, that means we will do the crossover later. Then of course you need to run it n times. This is a mechanism that in the original proposal, but gradually is replaced by many other new mechanisms. For example, in David Goldberg's book in 1989, he already proposed a mechanism which actually is simpler to implement, but he also finds it more efficient. Okay, now what does this do? It's very simple. It's called tournament. The tournament is you still based on randomization, but you randomize choosing chromosome. Okay, and then you choose 2 of them, and if the size of the tournament will be 2, you call binary tournament. So let's say that you randomly choose 2 solutions, and then you compare which one is better, and then you select the one that is better. And of course, you will repeat this step until you find a set of solutions that you can do the populations. So this is something called a tournament selection, which is more popular today compared to volatility wheel selections. So what happened after you made the selections? You will go for the evolution and genetic operators. We talk about crossover is some sort of weak combinations, and then mutation is performing a random walk to introduce the diversifications, to introduce this diversity in order to do explanations. So let's see, I think the best way is to look at how the crossover and mutation work for the binary string. Originally, you have the binary string. Later, we will show you how it works with a real number. But for a binary string, if you have a 1-point crossover, single point crossover, you randomly choose where you want to cut. But after you choose where to cut, then the first part of the genes coming from the first chromosome, as you can see here, but the second part is coming back from here. I think it's better if I give you a pen here so that you can see okay, now the PowerPoint will lay a bit strange, but I try to show you how the first part and the second part is preserved from the first part of the parent, but then you swap in the second part here. And of course, you can go for this kind of 2 points. And later we will show that you can also do uniform. And that means each of the particular gene component is actually can be swapped, not only like you make the whole string. And then to those kind of uniform, they are also usually useful, especially you aiming at something that you want to preserve certain order. Now for the mutation, the mechanism is different because of now you don't need to have the both parents. You just have individual solutions. And then each of the particular bits there, you will try to flip. Let's say that you flip based on your populations of the mutations. Sorry, the probability of your mutation. But if you flip each of the bit and then you find that by that bit you need to do the mutations because of the low probability, then you will see that now in this case this bit is mutated. So across this X bit here, there's only one bit that is mutated. So I think quite quickly we have gone through the concept about selections and also mutations and also the basic genetic algorithm. And then when we come back from the break, then we will look at something more practical because of this set of operators are something you could choose not only in Facts Analyzer, but also some other software. So when we come back from the break, we will continue to look at about more advanced crossover and mutations. Do you have any questions to me?